Okay, so question 7. The Lewis structure for carbon disulfide is shown below. What are its electron pair geometry and molecular geometry around the central atom? So let's draw the carbon that has 2 double bonds to 2 sulfur atoms. And the central atom is carbon. So I'll take note of how many lone pairs it has and how many bonding pairs it has. So carbon has 0 lone pairs, and by bonding pairs it means the 2 sulfur atoms. So 2 bonding pairs. So now let's look up what type of Vesper shape it would have. Oh, I think yeah, VSEPR. Okay, so the nice chart. So these charts are usually given in the question or like during your test, like in one of the back pages. So the number of lone pairs is 0, and the number of bonds or bonding pairs, or you can call it charge clouds, is 2. So we have a linear molecular geometry. So instead of bond pairs, I'll also denote it as charge clouds. So some tables might refer to them as that. So therefore, CS2 has a linear geometry. And it also has sp hybridization. So I can show that with another table that might show everything. Sounds nice, but it's just like small. Yeah, so this is one of the good tables that shows almost like everything. They show the bond angles, and they also show what type of hybridization it is. So it's pretty small. Okay, here we go. Yeah, so again, we have a generic formula, AX2. The picture looks like kind of like linear. So 2 bonded atoms, 0 lone pairs, and sp hybridization. And they even have the bond angle, which is around 180 degrees. I'm going to write that down as well. Okay, so this is the Vesper theory, which kind of estimates the type of shape a molecule may have. And let's see what the junior tutor said. Oh, they had their own table here too. Hybridization occurs to ensure that the resulting molecule is stable. That is done by minimizing the repulsion between the electron groups, so bonding groups and the non-bonding electrons. As a consequence of this, molecules have to conform to a specific shape that maximizes the distance between the electron groups. Generally, the number of hybrid orbitals depends on the number of electron groups present. For instance, if an atom has 5 electron groups surrounding it, it needs to hybridize 1s, 3p, and 1d orbitals. This yields 5 degenerate, equal in energy sp3d hybrid orbitals. And to maximize the distance between the electron groups, the shape should be a trigonal bipyramidal. So this is shown like here. And before we proceed to the problem, let us first differentiate what electron or molecular geometry is. Electron geometry refers to the shape when all the electron groups are included, both bonding groups and lone pairs. Meanwhile, molecular geometry considers the shape of all the bonding groups only. The 6 commonly tackled hybridization are shown below with the shapes associated with these. Possible molecular geometries of each hybridization are also provided. Okay, so this is a nice graph that they have, or table. And you can see the linear geometry that we have. And then based on the Lewis structure, there are 2 electron groups in carbon disulfide, 2 bonding groups, and 0 non-bonding. If the number of non-bonding groups is 0, the electron geometry and molecular geometry will be the same. Referring to the table above, since there are 2 electron groups, it must be sp hybridized, and its electron and molecular geometry must be linear. Yep. So this solution is correct. It was very well explained and in depth.